In this video, we'll discuss another unsupervised learning technique, dimension reduction with principal component analysis. This is a lot of new words, so let's start with some motivation. Suppose we have a set of data on 100 different restaurants. For example, for each restaurant, we have information about its Yelp rating, its rating on Google, typical wait time for a table, its zip code, neighborhood, city, whether it serves tacos, and so on. Suppose our primary goal is to just better understand the structure in this dataset. That is, we don't have any y response variable which we hope to predict or classify. Thus, this is an unsupervised learning task. Within the unsupervised setting, we might be interested in exploring the similarities among the restaurants, or rows in the dataset. This is a clustering task. This cluster analysis might reveal distinct clusters of restaurants. For example, there might be a cluster of restaurants that are more popular and a cluster that are less popular. We might ask similar questions about the features or columns of our dataset. Specifically, if we can identify similarities or correlation among the features, then we might be able to collapse or combine these into a smaller set of uncorrelated features without losing a significant amount of information. In fact, you likely already picked up on some structure among the features. For example, the first three features provide different measures of popularity. It's reasonable to assume that these will be correlated. Thus, maybe we don't need to keep track of all of them. Similarly, the next three features provide different measurements of location. And the last set of features provide different information about the food offered at each of the restaurants. In summary, then, maybe it's not necessary to keep track of all of these features. Rather, maybe we can collapse these multiple predictors or features into a set of just three: a popularity feature, a location feature, and a food feature. Notice before moving on that this is very different than variable selection techniques such as backward stepwise selection and lasso. Those techniques simply kick out some features. What we're talking about here is combining features. In general, suppose we have high-dimensional data with p features, x1, x2, up to xp, where p is really big. That is, we have lots of features. Beyond our restaurant example, high dimensionality is common among genomic and genetic data sets, image data, video data, satellite data, and more. In such scenarios, dimension reduction can help us to identify structure and patterns among the features. Mainly, if we have lots of features, we can't use simple numerical and graphical summaries to explore the relationships among them. For example, suppose we merely wanted to plot the relationship among every pair of features in a dataset. Now, examining 10 features would require 45 plots. Examining 20 would require 190 plots. And if we had 150 features, we would need to make more than 11,000 plots in order to look at every pair. Next, storing, transferring, and analyzing mega datasets is resource intensive. By reducing the number of features in our dataset, dimension reduction can help us to conserve computational resources. Finally, unsupervised dimension reduction techniques can actually facilitate supervised regression and classification techniques. Suppose that we wanted to use lots of features, x1, x2, up to xp, in a regression or classification model. On top of the considerations above, that is, on top of conserving computational resources and helping us identify structure, dimension reduction eliminates the complication of working with multiple correlated or multicollinear predictors. Further, in some cases, p is actually greater than n. That is, we might have more predictors than we have data points. In this scenario, our regression and classification models just break down. We can't actually run a model with p greater than n. Thus, dimension reduction would help us collapse the original features into a smaller, more manageable dataset. That is, dimension reduction would actually help us implement regression and classification. It would make it possible. To see dimension reduction in action, consider a simple example in which we just have information on two features. Here are the Yelp ratings and Google ratings for 13 different restaurants. As you might expect, these ratings are strongly correlated. That is, if a restaurant has a high rating among Google users, it tends to have a high rating among Yelp users. In general, recall that the goal of dimension reduction is to combine a set of correlated features into a smaller set of uncorrelated features without losing a significant amount of information. Or, in this simple setting with just two features, we want to combine the correlated Yelp and Google ratings into one feature without losing a significant amount of information about the popularity of a restaurant. To simplify this process, we're going to work with centered data. That is, we subtract the mean from the Google ratings and the mean from the Yelp ratings, so that they now both have mean 0. Now, in order to turn these two features, Yelp and Google ratings, into one feature, our first instinct might be to just kick one of them out and keep the other. For example, suppose we just kept the Google ratings. This is analogous to trying to take a picture of our restaurant data by standing at the Google axis. That is, we're not really looking at the data head-on. And from this point of view, some of the restaurants are hiding behind each other. That is, not all restaurants with the same or similar Google ratings will have the same or similar Yelp ratings. Here we see that there are 3 restaurants that all have the same Google rating of around -0.1. However, these 3 restaurants have relatively different Yelp ratings. But when we take a picture from the Google axis, the only information we retain is the Google information, and so we lose all of the variability in the Yelp observations. Thus, if we keep only the Google ratings, another way to think about this is that we lose information about all of the variability in Yelp. Similarly, if we only keep Yelp ratings, we lose information about the variability in Google ratings. And in general, if we just kick out a feature from our dataset, we'll simplify or reduce the dimensions of the dataset, but we'll lose more information than necessary. So let's consider a more careful idea. Instead of simply kicking out one of our original features, we can find the direction along which we get the best picture of the data. Now, a good picture is defined to be one that preserves the greatest variation, or the most information, in the restaurants. For example, if we take a picture of the data from this angle, we do a little bit better than before, than taking it from Google straight on. There are fewer restaurants hiding behind each other, but in terms of capturing more variability or more information, we can do even better. In fact, this is the direction from which we can preserve the greatest information in our picture of the data. Let's dig into the details a bit. Notice that what we've done is rotated our original Yelp and Google axes, producing 2 new axes. These axes correspond to 2 new features, which are called principal components. We'll label these as the first principal component and second principal component. Further, these 2 new features, or principal components, are linear combinations of our original 2 features. For example, the first principal component is obtained by 0.678 times Google rating, and then adding 0.735 times Yelp rating. The second principal component is obtained by 0.735 times Google rating minus 0.678 Yelp rating. Thus, we can express the information about each restaurant relative to both of these coordinate systems. For example, take this restaurant here. This has a centered Google rating of 1.31 and a centered Yelp rating of 1.28. By plugging these original features into the formulas for the principal components, we can get the coordinates on the principal component scale. In this case, this restaurant has a coordinate of 1.83 on the first principal component and 0.1 on the second principal component. Again, we obtain these by plugging our original values of 1.31 Google rating and 1.28 Yelp rating into our principal component formula. Next, the coefficients in the linear combinations that define our principal components are called principal component loadings. For example, principal component 1 has loadings of 0.678 on Google and 0.735 on Yelp. Finally, notice that this first principal component is the direction of maximal variation. The points are very spread out along this feature. The second principal component here was chosen to have maximal variation among the direction that's orthogonal to, perpendicular to, or uncorrelated with this first principal component. That is, it's capturing the information that goes in the opposite direction as the first principal component. Now that we've seen some of the details, let's step back and consider what we've accomplished. We started our analysis with a set of raw data on Google and Yelp ratings. When thinking about simplifying this dataset while preserving the information in it, we're concerned by preserving the variability in this dataset. To this end, we can get a sense of the variability in any feature by averaging up its squared observations. In total, the total variability in our original dataset is 2.042. Roughly half of this variability is explained by either feature. Specifically, the variability in Google ratings is roughly 0.942, and the variability in Yelp ratings is slightly higher at 1.1. And again, these add up to 2.042. Further, there's very strong correlation between the Google and Yelp ratings. In the second step of our analysis, we transformed our original two features into two principal components, the first and the second component. For simplicity, I've rotated that data here. Nothing has changed in the data itself, just our point of view of the data. All of the original information is still preserved. In fact, the total variability across both principal components is still 2.042, the same as it was before. However, the composition of this variability is different. Almost all of the total variability is now explained by the first principal component. Its variability is 2.004. In contrast, very little of the variability is explained by the second principal component. Its variability is only 0.038 of the whole variability in the dataset, 2.042. In fact, we can see that phenomenon here. We see a lot of variability in this direction, and very little variability in the second direction. Further, take a look at the relationship between the first and second principal component. Actually, there's not really any relationship to look at. The correlation between these components is zero. That is, they're completely uncorrelated. Now, given that we've been bogged down in the details here, you might not have noticed our success. Mainly in changing the direction of the data. First, we haven't lost any information or variability. That is, our total variability is the same as before, and we've removed the correlation among our features. We can take our success one step further to perform dimension reduction. Given that the majority of the variability in our transformed dataset is explained by this first principal component, or in this direction, then we can consider kicking out the second principal component altogether and just retain the information on the first. When we do, we can still explain almost all of the variability in the original dataset. Here, we've preserved a variability of 2.004 of our total 2.042, so we've done pretty good. And we've reduced the dimensions of our dataset from 2 features to 1, where this one feature preserves almost all of the information in our original data. So let's try these same techniques in a slightly more complicated example. Suppose we start with 3 features in our dataset instead of 2: restaurants' Yelp ratings, Google ratings, and location or longitude. The plots here exhibit the relationships among these 3 features. Mainly, we still see that there are 2 measurements of popularity, Google and Yelp ratings, and that these are highly correlated, as we can see in both sets of plots. Further, we see that location or longitude is related to the Google and Yelp ratings, but less so. It's a more moderate correlation. That is, longitude then gives us some restaurant information that the rating features do not. As before, our primary concern here is preserving the information in, or the variability in this raw dataset, but making it more simple. Here, the total variability across all three features is 3.305. The majority of this variability is explained by the longitude of the restaurant. Further, we saw that there's correlation among these three features. Though there's only moderate correlation between a restaurant's ratings and its location or longitude, there's a strong correlation of 0.952 between our two rating features. Principal component analysis can help us combine this overlapping information into a set of three uncorrelated features. In step 1 of our principal component analysis, we identify the direction that preserves the maximal variation or information in the dataset. This is the first principal component. Next, we identify the second principal component, which has maximal variation among the direction orthogonal to or uncorrelated with the first principal component. Finally, we identify the third principal component, which has maximal variation among the direction uncorrelated with the combination of the first two principal components. The scatter plot at left is simply our original dataset, but rotated in the directions of these three principal components. The plot at the right allows us to better inspect the relationship among each pair of these three principal components. Now, unlike the original three features, Yelp ratings, Google ratings, and longitude, we can see that these three new features exhibit no correlation. We don't see any patterns in the relationships among these three variables. That is, they each contain unique information about our restaurants. As before, these three principal components are the linear combinations of our original three features. So I can write the first principal component as the linear combination of Yelp ratings, Google ratings, and longitude. Further, the three principal components preserve the total variability of 3.305 in the original dataset. By design, the majority of this variability is explained by the first principal component. It explains 2.551 of 3.305. The second principal component also explains a significant proportion of this variability. However, the third principal component explains very little of the variability. Thus, maybe we don't need to keep the third principal component. Finally, there's no correlation between any of the principal components, just as we had seen in the plots before. In the final step of our analysis, let's consider how to use these principal components. Remember that we started with three features, which had a total variability of 3.305 and high correlation. Our goal was to simplify this dataset, that is, to combine these three correlated features into a smaller set of uncorrelated or less correlated features without losing much information in the process. If we had approached this the simple way, by say, kicking out the Yelp ratings, we would succeed in simplifying the dataset from three features to two features. However, we lose a significant chunk of the variability or information in the data. The variability here dropped from 3.305 down to 2.693. Further, though we got rid of Yelp ratings, which are strongly correlated with Google ratings, there's still a relatively moderate correlation among our two remaining features, a correlation of 0.473. Principal components analysis lets us do something more careful and thoughtful. We've transformed the three original features into three principal components. However, we saw that the third principal component explained very little information in the dataset. Given its lack of information, we can kick it out of our dataset. Thus, we're left with two features, the first and second principal components. Not only have we exceeded here in reducing the dimensions of our dataset from 3 to 2, we've lost almost no information in the process. The variability dropped very little, from 3.305 in our original dataset to 3.276 in our reduced dataset. Further, we've reduced the correlation among our features to 0. In summary, we've simplified our dataset from its original form in which we had 3 highly correlated features to its new form with 2 uncorrelated features. To wrap things up, recall that the goal of a principal component analysis is to turn the original set of P correlated features into a smaller set of K uncorrelated features, what we call principal components. Further, these principal components preserve the majority of information or variability in the dataset. Of course, there are some trade-offs to principal component analysis. Relative to this idea of simply kicking out some of the original features X, principal component analysis preserves more of the information in the original data. It's doing something more careful. However, PCA leaves us with a set of features that have lost their original meaning. Thus, it can be difficult to interpret the principal components. They're no longer on the original scale, but are linear combinations of our original features. Finally, in class, we'll consider more of the details behind principal component analysis. We'll use score plots to examine the relationships among the principal components. And we'll use loading plots to better understand how the principal components are constructed from the original features, thus how we might interpret them.